Hello and welcome everybody to the fourth video on this channel. In this video we're going to be going over an example using the thrust force and air resistance. So in this video we're just going to be solving a differential equation, but it's not really just going to be me solving a differential equation. It's going to be a lot about how you deal with changing mass systems and stuff like that, and how to connect two different differential equations together, because we're going to consider a rocket propelled car here, right, with some finite amount of fuel, and once it expends that fuel, it's just going to coast, right? And what we're going to do is figure out the motion as it's being propelled by the rocket, of course, and then of course the motion after it runs out of fuel. And how do we connect those differential equations together to produce one smooth position function? So that's going to be the goal. And I believe this video is going to be a little long because there's going to be quite a bit of steps to solving these differential equations, but oh well. So you may skip this if you like, if you kind of already know how to solve differential equations. It's not really going to be a theory video. But yeah, so let's get started. So we're going to say that the initial mass of this rocket is going to be m naught, and we're going to split the mass into two parts. We're going to have the mass of the structure itself and the mass of the fuel. So the mass of the structure is just the mass of the car with an empty tank, and the mass of the fuel is just, of course, the mass of the fuel. We're going to assume that the mass is going to be changing like this. So the mass does depend on time, and it's going to be a linear relationship like this. So as you can see, as time progresses, it's going to be losing a mass from its m naught, and this k is going to be assumed to be positive, and it will have units of kilograms per second. So you can think of this k as the rate of change of the mass, like how fast we're throwing the mass out. So like after, let's say k was 1 kilogram per second and time was 5, then that means we have lost 5 kilograms worth of mass. We spewed it out there. We're also going to assume that the exhaust velocity will remain constant throughout its first stage of burning. So it's going to spew the mass out at a constant velocity. So we don't have to really worry about it having time dependence. But you can make it a function of time. But it's going to make the differential equation more complicated. So let's not do that. And now we need to figure out the upper bound for time for the first stage, because we need to find out exactly how much time can elapse, right? Because once it burns all the fuel, then that means we cannot use a certain differential equation anymore. So this KT, right, is the amount of fuel that we have lost so far. We're going to split that m naught into ms plus mf minus KT. So once this term is 0, and we're just left with the mass of structure, we can't have we can't go past that in terms of time. So our upper bound would be t, or it will be this. And this whole thing has to be greater than or equal to 0. Right? So we can't have this be negative, because that means we would burn more fuel than there was. What we get by solving this is just that the time has to be less than or equal to mass of the fuel over k. That's going to be our upper bound. That's the maximum amount of time we can burn before it runs out of fuel. So that's going to be important. And we'll just make that bound right here. mf over k. There you go. So let us consider the first interval while it's burning the fuel. So that's going to be from time equals 0 all the way up to this upper bound that we just calculated. Once it runs out of fuel, once it reaches this time, it will have run out of fuel. So the differential equation for this is going to be pretty simple. Write this in red. We get mv dot, and then we're going to have the thrust force here, and then we're going to have the air resistance force, because we know what's going to happen if there's no air resistance. What we're really interested in is when the car is subjected to a lot of air resistance. So when it's going really fast, it's going to be colliding with a lot of air, and it's going to be slowing it down drastically. So in this case, we cannot neglect air resistance. And even if there was no air resistance, it wouldn't be really interesting to see what would happen, right? The car will just like speed up really fast, and then it will stop. It will just accelerate at a constant rate. So in order to account for the air resistance, we add the quadratic air resistance term. And you don't really have to understand what this is or why it's squared or anything like that. Just know that there's two different types of air resistance. There's a linear air resistance. We often just use that B coefficient as the drag coefficient. However, this linear air resistance is not really accurate for large macroscopic objects. It tends to work very well for very small, tiny little particles. But for large objects, the quadratic air resistance term is much more accurate. The B term pretty much just goes to 0, especially for a rocket car going really fast. This B term is going to be pretty much 0. And what we're left with is the quadratic air resistance. So just know it is much more accurate to model the air resistance as a quadratic. It's going to make your differential equations a little bit harder, but it'll be more accurate in the end. There you go. So that's the differential equation for that interval. So now let us consider the time after. So t is just greater than this upper bound. And it doesn't matter that it's equal to, because we're going to be matching the velocities anyways. We can't just have the velocity jump from one to the other. It has to be continuous. The acceleration might not be continuous, because once it stops exerting the fuel, it will change the acceleration suddenly, and that's going to be represented as a little discontinuity like this for the velocity here. Not a discontinuity, but a derivative discontinuity. But the position is going to be continuous. Alrighty, let's get rid of this. So after it runs out of fuel, the differential equation is going to be pretty easy. It's just going to be the force is equal to the air resistance. Now there's no more thrust. It's ran out of fuel, and the mass is also very important. We got to say that's going to be the mass of the structure, because once it runs out of fuel, it's going to be bone dry, and we're just going to be left with the mass of the structure. So that's going to be the differential equation for after. And now let us get to solving it. That's going to be in the next video. This is just simply the setup. So now that I've given you the setup, you can try for yourself. I will warn you that you will not be able to find the position analytically, but you can't go as far as the velocity. And I'm just going to post the answers right here. I think I spoiled the answers in the last video. This is going to be how the equations are going to look like. As you can see, we have the K, we have the exhaust velocity, we have the C, which is a drag coefficient, and as you can see, the higher the C, the more air resistance there is. And if we make this approach 0, there's going to be very little air resistance. There is a discontinuity at C equals 0, but at C equals 0, that just means there's no air resistance, and we didn't even have to include the air resistance term anyways. So we're not really interested in what happens when there's no air resistance, right? So as you can see, there's a very sharp decrease in the velocity. So this red represents the velocity, and this blue is the position. As you can see, I didn't calculate the position analytically, because look at the velocity function here. We're just taking the integral from, I know this says x, but that's just because the graph needs an x in order to graph it. But this is actually at time. Remember that this upper bound is going to be the time. It's going to go from 0 to t, and the initial position is going to be 0. So it starts at 0, and the initial velocity is going to be 0. One other important thing to note if you're going to attempt to solve this problem is that I'm assuming that the v0 is equal to 0 for the car. This is going to make the solving for the velocity much easier. So just remember that we assume that the velocity starts at rest as well, and it will start at 0. So there you go. Attempt to solve it. We'll be going over the solution in the next video.